Welcome back, class. Today I want to continue on our discussion, chapter 14, and talk about something called colligative properties. So colligative properties are properties of solutions, and they're unique because they only depend on the number of solute particles dissolved, not what those particles are. So it doesn't matter whether those particles are ions, doesn't matter if they're individual molecules, right? It only depends on how many of them, not what they are. And so in other words, the value of these colligative properties is dependent on the concentration of the solution. And so when we think about these colligative properties, the one thing you need to keep in mind is we're always comparing the value of that particular property of the solution that we're dealing with and the pure solvent, right? That's sort of the baseline, right? So it's how the property of the solution changed relative to that of the pure solvent. Now, a lot of times, right, the differences are based on somehow altering the attractive forces of the solute and how between the solute and the solvent. Because remember, the difference is when you create a solution, right, you're disrupting that pure solvent, right, and how the solvent had a certain kind of interactions with itself. Now you're replacing those solvent-solvent interactions with solute-solvent interactions. And so the difference between those interactions often will lead to the differences that we observe in these properties. Now, as we go through this, we need to remind ourselves of what happens when things dissolve. So if I dissolve a molecular compound like sugar, like glucose, right, we know that that breaks apart into individual glucose molecules. So let's say I dissolve 1 mole of glucose molecules, right? I'm going to end up with 1 mole of particles in solution. Now, what we have to then realize is that unlike molecular properties, particles, or molecular compounds, if I have an ionic compound, right, it breaks into multiple parts. And so when I dissolve sodium chloride, for example, if I dissolve 1 mole of sodium chloride, right, what I end up with is not 1 mole of sodium chloride particles, but end up with 2 moles of sodium chloride particle, right? Because every mole, right, 1 mole of NaCl generates 1 mole of Na plus ions and 1 mole of Cl minus ions. So 1 particle generates 2 particles, right? And so this is going to become important later on when we look at these colligative properties for ionic compounds, that, remember, it's the number of particles that's generated. So we're going to have to keep that in mind. Okay, so now that we have a basic idea of what a colligative property is, right, let's start looking at some colligative properties. So the first one I want to turn our attention to is vapor pressure. So remember, vapor pressure, right, is that pressure that develops above a liquid. So we went through the idea, we talked about evaporation, right, of if you put a liquid in a closed container, that it evaporates until it builds up a certain pressure of the gas that'll start to condense, and at some point you end up with dynamic equilibrium, right, where you have a certain amount of vapor and a certain amount of liquid, right, and at that point it doesn't change, right? That's the pressure exerted by this vapor is the vapor pressure of the pure material. Now, how does that vapor pressure, or the amount of vapor present, change if we create a solution? So if I take this pure material and I add some solute to it, so now all of a sudden, some of these surface positions, right, where evaporation takes place, are occupied by solute. And if for the moment, if we assume that the solute isn't volatile, meaning it doesn't evaporate, right? Let's say we've dissolved some solid, and so, but it's going to occupy some of these positions, right? Because we're going to have those solute-solvent interactions. So we have fewer solvent molecules at the surface, which leads to lower vaporization. So we slow down the rate of vaporization, but notice the condensation doesn't change. Right? Eventually, right, we will reach a new state here where we reach a new equilibrium, but that new equilibrium will have fewer particles of vapor and therefore a lower vapor pressure. And so we have the general conclusion that the vapor pressure of a solution is lower than the vapor pressure of the pure solvent under the same conditions. So in other words, at the same temperature. So we have this phenomenon of vapor pressure lowering of solutions compared to the pure solvent. So that's our first colligative property, vapor pressure lowering. Now, we can demonstrate this idea and sort of tie it back to our idea of spontaneous mixing. So if I take a container of pure solvent and a container of solution, and I put them in the same container, my assumption or my assertion is that the vapor pressure here is lower than the vapor pressure of the pure. So what spontaneous mixing tells us, right, is that over time, nature should try to equalize the concentration here. Well, we can't, obviously, right, because this one has solute and this one has solute, this one has no solute. But it can try. And the way that it can try is to lower the concentration here, which gets it closer to here, right? The concentration of solute here is 0. So if we lower the concentration, we're going to try to get these closer. So how does that happen? Well, the vapor pressure, we have a certain vapor pressure here, and it makes its way over here. And so lower vapor pressure. Okay? So we're going to build up vapor pressure. The vapor pressure starts to rise here as this evaporates. So what do? We get more condensation here to try to lower the vapor pressure back down again. And so we start building up solution here, right? We start building up more liquid to try to keep this vapor pressure low. But because we keep losing vapor into the liquid here, this vapor pressure then starts to drop, so we get more evaporation to try to keep the vapor pressure high here, and we just get this cycle, right, which leads to sort of the net transfer of liquid from here to here, equalizing or moving toward equalizing the concentration of these two solutions. So we get that transfer of solvent, right, and it's, goes back to this idea of spontaneous mixing. And it also proves that the vapor pressure is indeed lower here, because if the vapor pressure was the same, then there would be no transfer, right? The vapor pressure would build up to what it's supposed to be here in the container, and that would be perfectly fine here, right? There'd be no reason to get condensation occurring in our solution to try to keep that vapor pressure lower. All right. So let's look at how we can sort of think about calculating such a thing. So it turns out that the vapor pressure of a volatile solvent, so we're assuming the solvent vaporizes, right? And every liquid has a vapor pressure, but we're looking at something that has a reasonable vapor pressure. So the vapor pressure of a volatile solvent above a solution is going to be equal to the vapor pressure of the pure. So when we say it's normal vapor pressure, right, this is the vapor pressure of the pure solvent times the mole fraction of the solvent. So you're going to see we're going to use our mole fraction version of concentration here. So for example, if we have pure solvent, right, the mole fraction is 1. Right? So 1 times this, that means, right, the pure solvent is equal to the pure solvent. But if we have a solution, then that means the mole fraction of solvent is going to be less than 1. And so the vapor pressure is, of course, going to drop down based on what fraction is the solvent. So as we add more and more solute, the mole fraction of solvent gets lower, the vapor pressure keeps getting lower. Now, we can think about it in terms of the change in pressure, right? So how much does it drop from the pure to the solution? And if I want to calculate the change, that's going to be the mole fraction of solute times the pure vapor pressure. So we can just calculate the vapor pressure of solution, or we can calculate the change in vapor pressure. And the only difference here is in this one we use the mole fraction of solvent, this one we use the mole fraction of solute. Bottom line, as I've talked about, the vapor pressure is directly proportional to the mole fraction of the solute. Right? The more solute we add, the less solvent there is, the lower the vapor pressure goes. Okay, so this gives us a way to think about calculating the vapor pressure in any given solution. Now, this can be done by using something called Raoult's law. So Raoult's law for volatile solutes. Right? So what we just saw was Raoult's law. But what if we come across a situation where we have a volatile solute? So if both the solvent and the solute can evaporate. So this commonly would happen if we have two liquids mixed together. So let's say we have gasoline and ethanol mixed together, right? Both the solvent and the solute have a vapor pressure. So the vapor pressure, the vapor above it is not going to be one, it's not going to be just the solvent. It's going to be a combination of the solvent and the solute. So the total pressure, so this would be our total vapor pressure here, is going to equal the vapor pressure of the solute plus the vapor pressure of the solvent. And each one of these terms can be calculated using Raoult's law. So the vapor pressure of the solute is the mole fraction of the solute times the vapor pressure of the pure. The vapor pressure of the solvent is going to be the mole fraction of the solvent times the vapor pressure of the pure solvent. So if we have two things that can create a vapor pressure, we can calculate them individually, and then if we add them together, we would get the total vapor pressure. And you can see the makeup of that vapor is going to be dependent on the mole fraction. So if these are 50-50, right, we have half the moles are from each, well then, we're going to get vapor pressure representing that. But we have to base it on the mole fraction of each component in our mixture. Now, ideally, we'd see something like this, right? So if at each extreme is our pure, right? So at this extreme, we have component B. So we're doing this in terms of component A. And so at one extreme where we have no A, right, we have 0A, right, the vapor pressure is going to be just equal to the vapor pressure of pure B. Right? So this is, the vapor pressure of pure B here. And here, this is going to be the vapor pressure of pure A. Now, as I adjust the mixture, we get a weighted average here, right? So if I have a 50-50 mixture, right, it's going to be, halfway, if I were to draw a line connecting these, it's going to be halfway in between. If we have more of B, it's going to rise closer and closer to pure B. If I have pure A, right, it's going to move to be closer and closer to the vapor pressure of pure A. So it's a weighted average, if you will, right, taking into account the fraction of one, the fraction of each component. Now, this is under ideal situations, right? Well, but of course we don't always have ideal solutions. So we can see deviations from this ideal Raoult's law. So the first deviation is when you form really strong solute-solvent interactions. So let's say we get, two materials that form really nice, strong intermolecular forces with each other, and so they don't, evaporate, let's say, as easily. And so we're going to get what's called a negative deviation. And so the observed vapor pressure, right, is going to be lower than what we would expect to be. So normally, right, if I had a 50-50 mixture, I would expect, this vapor pressure. But because of the strong interactions, right, I get less evaporation, and so my actual vapor pressure is lower than what I would expect it. So having strong intermolecular forces gives a reduction in vapor pressure based on what you would calculate using Raoult's law. If you have very weak interactions, you get a positive deviation, meaning you actually get more vaporization than what you would see if you had the pure materials. So this is a case where you have weaker interactions than what you have in the pure material. So you get higher than expected vapor pressures. So these we don't see too often, or we don't look at them too often. This is going to be the normal situation. So this is what you're going to normally calculate using Raoult's law. You're going to calculate this ideal scenario. Okay, so let's pause right here, and we're going to do a sample problem. Okay, so let's look at a problem using Raoult's law. Now, this is going to be, of course, ideal situation. We're not looking at deviations here. So I'm going to calculate the vapor pressure at 25 degrees of a solution containing 55.3 grams of this compound HOCH2CH2OH in 285.2 grams of water. And I'm told that the vapor pressure of pure water, right, the pure solvent, at 25 degrees is 23.8 torr. And that's a pretty common unit that you'll see for these kinds of problems, torr millimeters of mercury, right? So if we recall our equation, right, so the vapor pressure of our solution is going to equal the mole fraction of the solvent times the vapor pressure of the pure solvent. So in this case, right, it's the mole fraction of water times pressure of pure water. Now, of course, the pressure of pure water, that's easy, right? We're told in the problem, it's 23.8 torr. The harder part here, the one that involves a little more work, is the mole fraction of water. So let's remind ourselves, right? The mole fraction of water equals the moles of water divided by the moles of solution, or the moles of solute. So I'm not going to draw out this whole thing. So this is what's called ethylene glycol. So I'm just going to, of Eg, right? So the solute plus the moles of water. So we need to calculate these. So first of all, the moles of water, right? We have 285.2 grams times 1 mole, 18.02 grams, right? So our moles cancel, and we end up with 15.83 moles of water. And the moles of Eg equals 55.3 grams times 1 mole. And if I add up the molar mass of this molecule, so add all this up, I get 62.07 grams per mole. So the 55.3 gram represents 0.8909 moles of Eg. So now I can do my mole fraction of water equals 15.83 moles of water divided by 0.8909 moles of Eg plus 15.83 moles of water. If we do all this out, we end up with 0.9467, right, as the mole fraction of water. So, as expected, right, our solution is mostly water, right, mostly solvent. So if I come back up here and calculate the vapor pressure of solution, we get 0.9467 times 23.8 torr, and you get 22.5 torr. So the vapor pressure has dropped from 23.8 down to 22.5, because now our solution is not 100% solvent, right? Like pure water, it's only 94.67%, if you will, water. Okay. So this is how we can calculate the vapor pressure of a solution using what we call Raoult's law. Okay, so in the next section here, we're going to look at some additional colligative properties.